Okay, today I would like to introduce my paper, Dijkstra-Based Selection for Parallel Multi-Lens Map Matching and an Actual Path Tagging System. And this paper was conducted by me, Changhen Lin, and Hongfu Ming, Boqing Liu, and Yuxiang Huang, and Zhongyou Shan. Okay, and here is the abstract. The abstract is that about a map matching problem is was dealt with a lot of people for a long time ago, and that we focus on the multi-lens problem, which can happen when the road network is pretty complex. And um, you can see the right picture, then you can see the GPS trajectory is not really accurate, and it people will be befuddled about the surface road and if that in the valid road at the valid road. Okay, and our algorithm can figure out what kind of road is most suitable for the trajectory. Okay, the introduction will be the German cars makers to acquire the Nokia here to enhance their digital maps and to get more traffic data. So the traffic data and the location based service will be more important nowadays. And if you want to get the traffic data and you want to know the traffic flow analysis, then you need to do the map matching in the most beginning. So that's why our works are valuable. And the map matching is a technique in the GIS that associates a sorted list of user or vehicle positions to the road network on a digital map. The main purpose are to track the vehicles, analyze the traffic flow, and finding the start point of the driving directions. And you can see the right picture. The input to GPS track and trajectory is not really accurate, so it must need a map matching algorithm. Okay, and here are two contributions about our paper. The first is a multi-lens map matching algorithm. And this kind of algorithm can deal with the highways, freeways, and expressways and trunks. And we can see in the following examples. And we convert the inaccurate road GPS data to the correct lane of a multi-lens road. Okay, and second, we developed a driver tagging system for actual paths, and this kind of system can provide a friendly interface for the drivers to track the predicted points to the predicted paths to the actual roads they passed, and it will provide the comparing best to a map matching problem, and it also will provide a correction to an OpenStreetMap. Okay. So this is a quick view of our driver tagging system, and we will also see the whole system, the whole website in the demo stage. Okay, and our tagging system allow the driver to track the green square points to the actual path they paced, and they traveled their path, and the black one is the GPS trajectory, and um, this graph is worthy to record to show is because here is a missing road of the OpenStreetMap data. Like the driver actually go the black trajectory, but there is no road for the OpenStreetMap data. So our algorithm can only connect it the whole way with the predicted path as a red line. Okay, and the following is the preliminary. A preliminary first we'll talk about the problem definition. The problem definition is like we want to identify the correct row segments combination and which we can construct a predicted path P for row GPS trajectory T in a given row segment GVE. And yes, there are many matching algorithms which are proposed, and we want to mention the most close one to us is the weight-based matching method. They propose the four factors. First is distance weight. It's like the nearest segments will be quite the most likely segments for the row GPS point. Okay. Second is a bearing difference. If the row segments bearing is quite different from the row GPS bearing, then it will get a low score or something. Okay, and third is the weight of the shortest path distance between two consecutive candidate row segments. So it will build a relationship between the two consecutive candidate row segments. Okay, then to give them the weights about the connectivity. So the third one is about connectivity, and four is a heading difference. If the heading is quite different. Is about the row data. Is a heading difference. Then maybe the row data would be wrong. It can be the error one. Okay, and this kind of algorithm got some problem. The total weight may be the same if the lengths are parallel lengths. So they will be the same when you only see the two consecutive points. Then maybe the weight-based algorithm can give you the same weight. And if the weight of the two segments are the same, then this algorithm can generate an unexpected result because it will not know which is the better row segments to select. And about a term definition, the first is a GPS trajectory. A GPS trajectory T is a point sequence from P1 to Pn, and each point is consisted with latitude, longitude, and time. Okay, and the row network is a directed graph GVE, and the V is the vertex and E is the edge. And we set the edge as the row segments and the vertex as the intersection of the row network. And each edge got the four properties. The first is start point E start and the ending point E end. And third is the row segment length E cost. And four is a row segment bearing E bearing. And it's like the angle. It's a row angle. The same thing. And the bearing is a north path and is measured clockwise. Okay. So the north will be 0 and the south will be pi. And a predicted path is a connected path. So the two vertices from the GVE will be VI and VJ, as you can see the white points. Okay, and the path is a set of the edges. Is from E1 to EN, and V1 VI is the E1 dot dot, and the VJ is the EN dot end. Okay. So you can see the concept I proposed previously. The green line is the predicted path, and about the property you can see a red line E5, and E5 got an EN and E star, and E cost will be 51.6 meters, and E5 bearing will be 270.3 degrees. Okay. And here is the algorithm. First, we need to form a candidate sets. And a candidate sets are generated by the near field cleaning and within the radius bound and within the bearing bound. And final, we need to check the heading coherence. Then we will generate a candidate row segment CRS. So here is a near field points cleaning. And the concept of this cleaning is pretty straightforward. It will just clean the near points. When the 2 points are really close, then this algorithm will just pick one as a representative point. So it's a downgrade sampling, and it will make the trajectory more precise because generally the GPS data is not really accurate. The average error will be 20 to 30 meters. So um, the additional points or of the near field may be a big problem for noise. And then we will use a radius bound and bearing bound, and you can just see the solid red line directly. This they are the CRS, and they are the remand row segments. They are within the radius bound and within the bearing bound. And you can see the gray circle means we only consider the row segments within this circle. And PI is the center, and PI bearing is calculated by the PI bearing from PI minus 1 to PI. And the heading coherence checking is the arrow which will happen in the road GPS trajectory. When the vehicle was stopped by a red light, it will generate this kind of situation. It will generate like 108 degrees back and forth, and it's totally wrong. So we just use a 3 point window to detect this kind of situation and to delete the sudden change occurrence. And here's the algorithm. First, we will input the row network and trajectory and the radius bound and bearing bound. And the output will be the CRS. So the first of three lines means that we use nearby searching and within the radius bound and to collect the row segments into the CRS. And the 4 to 8 means the bearing difference, and we will check the row candidate row segments set bearing and with the bearing of the p consecutive two consecutive points bearing. And if the bearing difference exists alpha, then the candidate's row segments will be removed from the CRS. And 9 to 13 is the three window detection for the heading coherence checking. And we use a simple weight uh, calculation to eliminate the anomaly. And after we form a CRS, then here is the concept of Dijkstra-Based map matching. The concept is that we got a lot of candidates for each point. Then how could we find a best combination for each point? And and in the beginning we use the speed or other ways to figure out which kind of combination is the best. But final, because of the connectivity concept, we think a new way, the whole way to consider all the combination is that we will form a new graph DSC on the CRS. So we will consider all the combinations of the candidate row segment set. And we just execute a Dijkstra shortest path on DSC again. Then we can get the selected row segment SRS, and which is the path shortest path coast, and it will be optima, is global optima shortest path candidate set is candidate row segment combination. Okay, here is a concept: a directed graph DSC Okay, and it will be a one-way graph. S1 means the point one, and S2 means the point two candidates. So S1 will be means that we have this three candidates for point one, and S2 means we also have three candidate row segments for point two, and so the combination between S1 and S2 between the point one and point two would be 3 multiplied 3, that means 9, and every age would be the Dijkstra connection cost between each candidate row segment. So after we build this kind of graph, we can just execute the Dijkstra shortest path again. Then we can find the shortest Dijkstra candidate segment combination. Okay. So here is the algorithm. First, we put the row network and the CRS as an input, and output will be a selected sequential row segment SRS. And this kind of segment will only map to one point, like point 1 map to CS11 and point 2 map to CS22. Okay. So the algorithm is the first line is define a new graph DSC, and the second is assignment. As second line to fourth line is the assignment to the new graph. So we will assign the CRSI to SIJI and assign the cost of Dijkstra from the CRSJ to CRSQ, and it's a proceeding propagation direction to the cost. Then at the line 5, we just execute the Dijkstra algorithm again on the DSC. Then we will get the set SRS. Then after we get SRS, the problem will be obvious. Then we just need to do the input interpolation, and we use the Dijkstra-Based interpolation to generate the predicted path. And the thought is quite simple. If we got the two candidate row segments which are not intersected, then we do the vertex of Dijkstra algorithm to interpolate all the points to the predicted path, and it's based on the network info GVE. Okay. So after we got this algorithm, then I conducted experiments from the questionnaire, and this is the interface of the questionnaire, and I got the positive feedback, and the 45 participants give me a mean of 3.72. It means that they are really confident about my predicted path. Okay, so here goes a demo. Okay, first I would like to ask my participants like their map reading skill. So maybe always, and it will affect a little bit about its effective survey or not. Then you can see this is a way you will is more accurate than the GPS trajectory. And I didn't put the speed info because I don't want you become confused in the legend. And the green is like a 60 to 70 kilometer per hour. Then yellow means 30 kilometer per hour. Yeah, and you can see, yeah, here is the work. So you can press just agree. Yeah, just agree. Yeah, it's kind of like this. Okay. And I also compare with the Mapbox map matching, and I just found some weird situation from the GeoJSON return type from the mailbox. It just got some missing information. And based on some examples, our algorithm will do better on the multi-lens situation, just like this. This trajectory it went under the elevated road and go to south. Okay, but as you can see at the top of the trajectory, the map box got some missing data. Yeah, and I don't know why. And so maybe our algorithm can um, contribute some correction for them. Okay. And here is the comparison with the driver tagged actual path. And the accuracy will be 1 minus the simple bracket. Okay, it's corrected points from drivers divided total points from the predict path. Means that if the last point the driver modified, the driver corrected, then accuracy will be higher, and we almost get 90% accuracy in the 30 predicted passes. Okay, so here's the demo. As you can see, the green point you can just drag the green point. Or we can see the truth first. The truth will be this, and you can see, oh, the driver may think, oh, I didn't pass as that way, I need to correct it, so use tagging. Then he can just drag this point back to this road. Okay, back to this road and view truth, and you can see this is a little bit different, and this tag again. You can drag. Okay, view truth. Okay, then it's smooth now. So I think this kind of tagging system can generate an actual ground truth, and it may help the OpenStreetMap to become better. So here is all my work, and thank you for your attention.